In today's problem, we have three semicircles fitted inside an equilateral triangle. We are tasked with finding the area of the red remaining part. We know that all three semicircles are equal with a radius of 1. Each one lies on a side of the triangle while its curved part touches the adjacent side. Also, there are no gaps between the semicircles. They touch each other perfectly. So if you want to try and solve it on your own, pause the video now and come back. All right, the first thing we need to do is draw a line from the center point of the green semicircle to the center point of the blue one. We can easily tell this length is 2 times the radius, or 2r. Since the semicircles are fitted inside, if we draw a line from the center of the green circle, it touches the side of the large equilateral triangle. We know this is a tangent line, meaning it hits at 90 degrees. If we draw a line segment from this tangent vertex toward the blue circle center point, we create a right-angled triangle. We know the hypotenuse is 2r and the height is r. To find the missing vertical side, we recall a basic yet vital math theory, the 30-60-90 theorem. This theorem applies to any triangle where the angles are 30, 60, and 90 degrees. It states that if the shortest side is x, the hypotenuse is 2x. The remaining opposite side is x times the square root of 3. Therefore, this line segment's distance is r root 3. Now, what remains are the two smaller segments, the top and the bottom. Before we calculate the top part, notice that a small triangle is created by 3 points. For this top part, we look at the corner. Since the radius meets the tangent line, it bisects the straight angle of 180 degrees into 2 equal 90-degree angles. Therefore, the angle for this new triangle is 90 degrees. Given that the main triangle is equilateral, the top corner is 60 degrees. Since the angles are 90, 60, and the remaining one is 30, we can for sure use the 30-60-90 theorem again. Here, we know the adjacent side is r. We don't need the hypotenuse, we only need the length of the opposite side. In this specific setup, our side r acts as the x root 3 side. To find x, we divide by the square root of 3. This gives us the height of the top segment as r over root 3. Now, only the bottom side is left. However, we need to find the specific angles to solve this. To do so, we can form a triangle connecting the following points: the bottom vertex of the main equilateral triangle, the blue semicircle's center, and the orange semicircle's center. To find the angle at the blue center, we have to look at the straight line along the side of the triangle, which equals 180 degrees. First, recall the 30-degree angle we found in the previous step. Next, if we draw a temporary inner equilateral triangle connecting the centers of the 3 semicircles, we know that each angle inside this temporary triangle is 60 degrees. So we have 30 degrees from the top and 60 degrees from the middle. To find the remaining angle, we subtract these from the straight angle of 180 degrees. 180 minus 30 minus 60 equals 90. This proves that the remaining angle is 90 degrees. Since we now have a 90-degree angle and the 60-degree angle from the main triangle, the final angle must be 30. This allows us to use the 30-60-90 theorem one last time. Here, the side with length 2r is the adjacent side, and we are looking for the opposite side. Since the adjacent side corresponds to x root 3, we must divide 2r by the square root of 3. This gives us the remaining bottom part as 2r over root 3.
Now we're close. Adding those 3 segments together gives us the total side length of the large equilateral triangle. That is, 2r over root 3 plus r root 3 plus r over root 3. To save time, when we add these up, the side length becomes 2r root 3. Since we are given that r equals 1, the side length is just 2 times the square root of 3. If we simplify that, it is approximately 3.46. Now we find the total area using the formula for an equilateral triangle. If we replace the side length with 3.46, the area of the triangle equals 5.18. However, we only need the remaining red space. We have 3 equal semicircles, which is equivalent to 1.5 full circles with radius 1. Since the area of a circle is pi r squared, and r is 1, the total area of the semicircles is 1.5 times pi, which equals 4.71. Therefore, the area of the remaining part is the area of the equilateral triangle minus the area of the 3 semicircles. 5.18 minus 4.71 equals 0.47. If you enjoyed this geometric puzzle, hit the subscribe button for more weekly challenges.